Respiratory Physiology, the mechanics of breathing. Welcome to our podcast, where today we embark on a journey into the fascinating world of breathing mechanics. In this episode, we will uncover the physical principles that guide every breath we take, from the gentle rise and fall of inhalation and exhalation to the intricate processes occurring within our lungs. Let us begin with the fundamental concept that drives pulmonary ventilation, the pressure-flow relationship. Breathing is a mechanical process, relying on pressure gradients between the atmosphere and the tiny air sacs of the lungs known as alveoli. Air moves naturally from areas of higher pressure to areas of lower pressure. During inhalation, the pressure inside the alveoli must fall below the atmospheric pressure. Conversely, during exhalation, the pressure within the alveoli must rise above the atmospheric pressure. A key law underlying this process is Boyle's law. This law states that, for a given amount of gas at a constant temperature, the pressure and volume are inversely related. When the volume of the thoracic cavity increases, the pressure inside decreases, drawing air into the lungs. When the volume decreases, pressure rises and air is expelled. This interplay between pressure and volume is the foundation of ventilation. Next, let us examine the respiratory pump, the muscles responsible for moving air in and out of the lungs. Inspiration is an active process, primarily driven by the diaphragm. When the diaphragm contracts, it flattens and moves downward, expanding the vertical dimension of the thoracic cavity and accounting for the majority of air intake during quiet breathing. Accessory muscles such as the external intercostal muscles, scalenes, and sternocleidomastoids assist during forced inspiration by raising the rib cage and sternum, further expanding the thoracic cavity. As these muscles contract, the thoracic cavity enlarges, the pressure within the pleural space becomes increasingly negative, and the lungs expand. This causes the pressure in the alveoli to drop below atmospheric pressure, allowing air to rush into the lungs. During quiet expiration, the process is mostly passive. The diaphragm and external intercostals relax, and the elastic recoil of the lungs and chest wall reduces the volume of the thoracic cavity. This raises the alveolar pressure above atmospheric pressure, causing air to be expelled. In cases of forced expiration, such as during strenuous exercise, additional muscles including the internal intercostals and abdominal muscles contract to further decrease the thoracic volume and more forcefully expel air. An integral component of breathing is the pleural cavity and the pressure within it. The intrapleural pressure remains negative relative to atmospheric pressure, which prevents lung collapse. This negative pressure is the result of opposing forces: the lung's tendency to recoil inward and the chest wall's tendency to expand outward. The pleural fluid provides a crucial linkage between the lungs and the chest wall, ensuring the lungs expand and contract in harmony with the thorax. Should air enter the pleural space, as in the case of pneumothorax, this negative pressure is lost, and the affected lung collapses, a condition known as atelectasis. Breathing is also influenced by two key physiological factors: lung compliance and airway resistance. Lung compliance refers to the ease with which the lungs can be stretched or expanded. High compliance means the lungs inflate easily, while low compliance, as seen in conditions like pulmonary fibrosis, makes breathing laborious. Surface tension within the alveoli plays a significant role here. The presence of pulmonary surfactant, secreted by specialized cells, reduces this surface tension, enhances compliance, and maintains alveolar stability. In premature infants who lack sufficient surfactant, breathing is extremely difficult due to low compliance. Airway resistance is primarily determined by the diameter of the respiratory passages. When the airways dilate, resistance decreases and airflow is facilitated. Conversely, constriction of the airways increases resistance and makes breathing more challenging. Factors such as lung volume and the action of various neural and chemical signals affect airway diameter and resistance. As we draw our discussion to a close, let us summarize the elegant mechanics at play each time we breathe. Inspiration begins with muscle contraction, increasing thoracic volume and drawing air into the lungs. Expiration relies on muscle relaxation and the elastic recoil of lung tissue, decreasing thoracic volume and pushing air out. In moments of exertion, accessory muscles amplify these movements, ensuring the body receives the oxygen it needs. Breathing is a beautiful interplay of physics, anatomy, and physiology. Each breath is a testament to the intricate systems that sustain life, a process so automatic, yet so vital. Thank you for joining us as we explored the mechanics of breathing. Stay tuned for more episodes where we delve into the wonders of the human body. It's the Everything Surgery Podcast. Dissect the extraordinary.